Swayam Prabha. Digital India. Educated India.
In the previous two lectures, we have been talking about basic inventory models. And in today's lecture, we are going to be talking about another kind of inventory, especially which is known as material requirements planning, MRP as it is often abbreviated as. Now, when we talk about MRP, we are going to be we must know what exactly MRP does. And I think the important thing to realize is that MRP is valid for those situations where you have, let us say, an assembly of parts and components, and we are talking about the master schedule of the end item. For instance, what it might mean is that suppose the schedule of cars that you want to produce is known, and then you got to plan out when to make the various sub-assemblies, how to assemble the various raw materials and so on. So from the given master schedule for end items, we are basically trying to determine the detailed schedule for the raw materials and the components used in the end products. So that is the primary purpose of MRP. That is, starting from a master production schedule, as it is called, of the end item. And since there are a very large number of end items, a very large number of raw materials and components involved in the end item, for instance, a typical car might have something like 8 to 10,000 components. So we have to actually plan for the procurement and production of all those components. And depending upon the master schedule, we find out when to procure, when to make the raw materials and the components which are used in the end product. I think the point to be noted here is that a typical MRP system, the demands that you are dealing with for the raw materials and the components are what we call dependent demands or lumpy demands rather than independent demands. That is the crucial difference between MRP and conventional inventory control. So when you try to make this distinction between independent and dependent demand systems, basically independent demand systems are those systems where the demand is unrelated to demand of other products such as end products or spare parts, etc. These are demands which are totally unrelated to the demand of the other products. These independent demands can usually be determined by a forecast. And conventional inventory control using EOQ or Wagner-Witten models are generally applicable in these situations. So when we talk about independent demand, normally EOQ deals with independent demand items. That means you are assuming that the demand for that particular item is actually determined by environmental factors and is not influenced by anything else. So you may then tend to use this particular demand for purposes of finding out what the either the forecast or what should be the lot size involved in such systems. But mind you, this will not be the situation when you are dealing with the raw materials and the components involved in a dependent demand system. So when you are dealing with dependent demands, the demand is directly related to the demand of some other product, such as components, raw materials or sub-assemblies, and the requirements are derived from the delivery schedule of the end items. And MRP is the appropriate tool for planning and control of manufacture inventories such as raw materials, work in progress, component parts and sub-assemblies in that sense. Just to give you an example, take the example of the car. In the car manufacture, which has a large number of components and raw materials needed, what you can say is that the demand for the car follows an independent demand. But when you are talking about the demand for tires, each car which is produced has 5 tires, including the stepney, and therefore if you have to produce 20 cars in a particular month, the demand for car tires during that month will be, in which you are assembling the car tires, is 100. So this is what we mean by demand. So the demand for car tires is actually dependent upon the production of cars in that sense of the term. So MRP systems are actually applicable in those situations where we are dealing with dependent demands and not independent demands. Okay, that's the point. We are given the independent demand of cars that we need, and we are trying to find out how many tires, how many steering wheels and how many other components we would be requiring during the entire period of production. Another very important feature of the dependent demand is the fact that the demand is lumpy, unlike continuous demand. For instance, if you take the economic order quantity or the economic lot size formula, what happens there is we assume that the demand is falling at a constant rate. The actual demand might not be falling at a constant rate, but the withdrawals might be few, so that actually the variation of the inventory level could be a staircase function of this kind, which you are actually approximating by an average rate of demand. So this is the kind of thing which we assume in continuous, when the demand is continuous. However, when you have lumpy demand would mean that suddenly there would be a withdrawal. For instance, if you in this particular period you are withdrawing suddenly maybe 100 tires, so the demand inventory, the inventory for tires suddenly falls from this point to this point, and then there is no further withdrawal, and then there is a withdrawal of a few items, and then this is constant for some time and so on. So basically, features of typical lumpy demands are, which are typical of MRP applications, that all these raw materials, components, sub-assemblies which are consumed in large increments corresponding to a certain batch of the final product. So this is a withdrawal which takes place when during this period there is a demand for so many units of this particular product. So this demand, which shows this kind of large increment, and which is showing, for instance, a sudden withdrawal and then no change, and then a small withdrawal and then no change and so on, this kind of situation is what we call a lumpy demand. So in a nutshell, we can say that typical demands in an MRP situation for the components and the raw materials are lumpy demands. I think the other aspect that you need to consider in an MRP setting is the typical definition of lead times, and normally we are concerned with two kinds of lead times. We are talking about an ordering lead time for purchased items or parts, and we are talking about a manufacturing lead time for those items which are actually manufactured within the company. For instance, in this case, all you have to do is you have to do the initiation of the purchase requisition at this point of time, and ultimately you get the receipt of the item from the vendor either off shelf or he fabricates it at this particular point of time. So this interval between the initiation of the purchase requisition and the receipt of the item from the vendor is actually called the ordering lead time. Similarly, when you are talking about a manufacturing situation, you place an order at this point of time internally for manufacturing something, and then you process the part through sequence of machines as given on route sheet, operation plus non-productive times, and the item is actually delivered to you here. So this difference then is actually the manufacturing lead time. In MRP, we require lead times because they are used to determine the starting dates for assembling final products and sub-assemblies, for producing component parts and for ordering raw materials. Because anything that you procure or produce has a time requirement or a lead time. So it could either be an ordering lead time for those items which are procured, or it could be a manufacturing lead time for those items which are manufactured. And you must, in fact, this is a typical input to the MRP system. So if you look at an MRP system, the major inputs to an MRP system are these three. Number one, the master production schedule and other order data for the end item. Because to run an MRP, you must specify how many cars or how many units of the final product you would like to have in different periods. So this is that master production schedule. For this, based on this information and also based on what we call the bill of materials file, the bill of materials file actually specifies the product structure. How many components, how many sub-assemblies are required to make the final product and how are they related to each other. This is actually the information which is available in the BOM file, the bill of materials file. And the third major input to the MRP system is the inventory record file. That means you must know what is the stock of different items, components, raw materials that you already have, so that when you are making purchases, you account for the materials that you already have. That's the basic idea. So these are the three major inputs that we have for the MRP system in this particular framework. Now, what may happen is we might have what are known as common use items, and these are the ones which tend to complicate the process of computation of the requirements of different types of products. For instance, we might be producing, say, n different products, P1, P2, P3 and Pn. These different products might be requiring different types of components. For instance, what is shown here is that P1 requires component C1, it requires C2 and it also requires C3. Whereas P2 requires only C1 and C2 and so on. It's like trying to say that if I'm making Maruti 800, Zen and other models of the car, some of the components could be common to various brands, others could be different. Okay, so that's what is shown here. And then a particular raw material, for instance, if they are all made of stainless steel, this particular component, basic raw material, could be common maybe to all these various components. Now this kind of information is basic information when you are dealing with MRP, because MRP collects the common use items from different products to effect economies in ordering the raw materials and manufacturing the components and the sub-assemblies. What do we say here? For instance, if you are trying to place an order for the component C3, the component C3 is required in the product P1, it's also required in the product P3, and it's also required in the product PN. So depending upon your requirements for these three products, you will have contributions to the product P3 from all these particular requirements, so that when you are either placing an order for purchase or manufacture of this component, all this will be in fact shown in this particular scheme of things. What is first, let's try to get an overall idea of what an MRP system would look like. So a typical MRP system, because the number of components could run into thousands, is generally a computerized system, and therefore a typical MRP system will have this kind of a structure. What it requires is information on the master production schedule. The master production schedule is generated from two sources. One is the customer orders which have already been placed, and then on the sales forecast that you have made. So sales forecast and the customer orders, when aggregated together, will give you the master production schedule, which will tell me what is the requirement of this particular product in the month of January, in the month of February, in the month of March, and so on. So this is what is a master production schedule, which is derived from basically these two bits of information. Then what we have is, we have a basic bill of materials file. The bill of materials file is kept update with any engineering changes. If you change the design of the product, for instance, that particular change in the design is captured here, and therefore it would be available in the bill of materials file. For instance, if you are deciding to either omit a particular component, then this would be shown in the engineering changes, and the bill of materials file will reflect this particular change. So this bill of materials file is the second major input to the MRP processor. And of course the third thing that we have is the basic inventory transactions. Inventory transactions would mean, this is like a accounting system. It's like your bank account. You take out so much money, you put in so much money, and therefore this is available to you at the end of this account. So similarly, inventory transactions show that as far as a particular raw material is concerned, you have so much in hand, and then you issue 50 tires, and then you probably buy 20 more tires. So what is the status of the inventory of that item for each of the thousands of items that you have, right? So inventory transactions will tell you what is the basic status of the inventory of different types of items, and this information is normally available in what is called an inventory record file. These are transactions. Each transaction takes place. A transaction is very much like the transaction that takes place in your each entry in your passbook in the account is a transaction. You withdraw money, you deposit money, right? These are transactions. But on the basis of that, you develop an inventory record file which is like your passbook, something like that. And then of course you have service parts requirements. Now these service parts requirements are the requirements of parts which are in addition to the normal requirements that you have for the product. For instance, if you sell 50 cars, then maybe from experience you know that you will have to sell some additional silencers and so on, which will be sort of replacements which are different. So for each item you will have some such requirement. So these are those, and ultimately these can be combined with the master production schedule because they define the requirements in that sense of the term. So these are the three major inputs to the MRP system. And then what does the MRP processor do? It gives you typically reports, output reports, and the most commonly used reports are these four. This is the most commonly used report. It's called the gross and net requirements report. That means it tells you what are the gross requirements of different jobs and what are the net requirements of different jobs. Capacity versus load report, which means it tells you that what is the capacity that you have and how much are you loading it in individual periods. Shop floor planning report is more detailed, and it tells you exactly how the various equipments and the machines in the shop floor are going to be loaded over the next 1 week, 2 weeks, 3 weeks. And finally, the production order status and exceptions report, which will tell you that as the processing keeps going, are you conforming to your requirements, or are you making any departures from the schedule? So this kind of information is also available here. So this is broadly the structure of an MRP system in that sense. Now we'll take up an example to see how exactly an MRP system would operate with a limited number of items, so that you understand the logic of how the computations actually are performed. But typically what we are trying to say is, what does a master production schedule look like, which is one of the basic inputs to the MRP system. A master production schedule will be a document like this, which will probably say that in week number 6, 7, 8, 9 and 10, product P1 you need 50 of them in the 8th week, and you need 100 of them in the 10th week. Similarly, this product you require 70, 80 and 25 in the 7th, 8th and 9th week. So like this, for each product, this is the end product, this is like the final product, this is like the car. How many Maruti 800s and how many Zens, etc. that I need in different periods. So this information is called the master production schedule, and this is the basic driver of the MRP system. Okay, and typically you can see what is the information that you get in the master production schedule. You get, number one, what end products are to be produced. It tells you product P1 and P2 are to be produced. Then how many of each product is to be produced, this tells you, and when the products are to be ready for shipment. So it basically specifies all these three things when you are talking about a master production schedule. When you talk about the demand, often demand will have, let's say, these three components. It will have the firm's customer orders, which are part of the demand, forecasted demand, which will be based on your forecasting system. So you have, this is the demand. The third thing that you typically have is demand for individual component parts for repair and service. Normally this component of demand is excluded from the master production schedule. So the master production schedule generally talks about only these two, right? But this could also be included, there is no problem, but typically when you are talking about a master production schedule, you have only these things. So this particular thing, demand for individual components and parts, is often excluded from the master production schedule, since it does not include end product demand. That's the reason, right? Because this is like a demand for only wipers, or demand for only additional silencers, or demand for only windscreens, broken windscreens which you are replacing. Now this is generally excluded because it does not emanate from the end product, it is an additional thing. Now we have seen what the master production schedule looks like. Now let's see what is a BOM file. What is a bill of materials file? A bill of materials file will typically be a hierarchical structure of this nature. At the level 0 you have the product, which is the final product P1. This product is composed of two sub-assemblies, S1 and S2, and there are numbers here which indicate that for each product I have one sub-assembly S1 and two sub-assemblies S2 which are needed to make the final product. Which means you can imagine that if this was the cycle, the bicycle, then you would have two wheels sub-assemblies to produce the bicycle, and maybe one frame which is required for making the bicycle. So 1 and 2 here refer to the number of parts of that type going to make 1 unit of that particular product. Then of course we have, at the level of the raw materials, we again have sub-assembly S1 is composed of C1, C2 and C3, and the numbers here show that 1 unit of component 1, 4 units of component 2 and 1 unit of component 3, they are all required to make 1 unit of sub-assembly 1. See, that is the notation. Similarly here, when we say 2 units of component 4, 2 units of component 5 and 6 units of component 1, these are required to make 1 sub-assembly S2. So since we need 2, we will have to double this particular value here. That is the notation. Then of course the sub-assembly S1, which is shown here, is said to be the parent of components C1, C2, C3. So this is the parent, and these are the 3 components. And any engineering changes affecting the product structure must be fed to the BOM file. That means if you are changing the design, what does it mean? You are either eliminating this component or making a different component or something. So these changes in the design will have to be reflected in the BOM file that you have with you. Okay. So we have looked at the master production schedule, which is of the end items. We have seen the BOM file, which is nothing but the product structure, how the product is composed. In fact, if you would recall your lessons from graphic science, when you do an assembly drawing, you typically develop a bill of materials with that drawing. What is that bill of materials? That's exactly this. It tells you how many components of each kind will go into the final assembly. So that's the information and how they will go into this. Then the third major thing which we need to understand is the inventory record file, because then these define the 3 major inputs to an MRP system. An inventory record file is important in the sense that it should give you accurate current data on inventory status. It should not have lags. If you want to find out how much money you have in the bank today, if your copy is not updated for the last 6 months, you will not be able to find this out, right? So what you need is an accurate current data on inventory status. Each inventory transaction is reflected, and then you can find out how much would be this quantum of inventory of different products you have. This is generally computerized in the form of an item master file. And in this, when we are talking about the inventory status, lead times must be established in the inventory record file. We talk about both the ordering lead times and the manufacturing lead times. So this comes from the purchasing records, and this comes from the process route sheets of the manufacturing that you are doing within the factory. So you should have this information on lead times corresponding to each item in the inventory, because when you are placing orders, you must know how much time it's going to take. And then of course the inventory transactions, which means the issue of material, the arrival of material, the order placement, the realization, must be kept current. So these are the basic requirements of the inventory record file. So now that we have a fair idea of the 3 major inputs which are required for an MRP system, we would like to work an example to see how this information can be utilized for solving this particular case. So we will take this example which has 2 end products, P1 and P2, and this is the BOM structure for 1 and 2. That means each product P1 is composed of subassembly 1 and subassembly S2. So 2 of this and 1 of this make the product. And similarly the subassembly 1 requires the components C1, C2 and C3, and similarly the subassembly S2 requires the components C4, C5 and C6. and in these quantities which are shown here. Okay, we can go down one level. We have the product level, the sub-assembly level, the component level, and then you might go for the material level, which is the purchased material. Say for instance, we are showing it only for this particular part. For C4 we have M4. So actually wherever C4 occurs, it occurs here also. So in this particular application as well as here, you are going to use this raw material M4. So this is the basically product structure for products 1 and 2, the BOM file. This is the master production schedule. The master production schedule states that product 1 and product 2, we require 50 in the 8th week and 100 in the 10th week, and for P2 it is 70, 80 and 25 in weeks 7, 8 and 9 respectively. So this is nothing but the master production schedule, which is the second thing, input required for this product. The third major input that we have to give is the initial inventory status, and suppose we are talking about various kinds of items. Suppose we are giving the initial inventory status for only M4, which is the item at the bottom of this particular BOM. So you would have information like, what this is saying is that scheduled receipts are, we are expecting 40 units of this item at the end in the third week. On hand we have 50 items. So once we have 50 items and 40 are going to be received in the third week, our stock level on hand will be 90 in the third week, because 50 plus 40. This kind of information is available to you as to, so this is like what is the inventory that we are likely to have of item M4 in the beginning. And then we would require information on lead times, because we require inventory status and lead time status, both of them together. For instance, what happens is P1 is the final product. This has to be assembled from S1 and S2. So P1 assembly takes 1 week. That's what we are saying. P2 assembly takes 1 week. S2 assembly of C4, C5 and C6 takes 1 week. And similarly S3, that is the third assembly, this takes 1 week. Then as far as item number C4 is concerned, which is required here and here at 2 places, this has to be manufactured, and it requires 2 weeks to manufacture this item. And the ordering of M4, which is the item at the end, this requires 3 weeks, because an outside vendor takes 3 weeks to supply this item. So this actually encapsulates the information pertaining to the product structure, the master production schedule and the inventory status for all the items. Okay. So this is the input. So we have now developed the input for our example, and let's see how exactly we would develop the detailed requirements for the various parts. In fact, the underlying logic of the MRP system is very sort of summarily described in this particular flow chart. What it shows is that you input the MPS, the master production schedule, the BOM file, the inventory status and the lead times. So we've got all that information. Then you do what is called parts explosion. We'll explain this when we come to the example. And after the explosion, you have to offset the requirements by lead times. So there is explosion, there is offsetting, then there is netting. Netting means my gross requirements are 100, but I already have 20. So I need how many? 100 minus 20, it is 80. This is called netting. What is my net requirement? It's as simple as that, right? And then finally, you may do lot sizing of the net requirements for procurement or production. So these are the basic steps which are involved when you have to do the MRP logic if you apply it for this particular situation. So you would begin this information we begin it from the end products, product 1 and product 2. We make a table like this in which we show the gross requirements, the scheduled receipts, the on-hand inventory, the net requirements and the planned order releases for each item. So as far as P1 is concerned, P1 has as a master production schedule where the requirement is 50 in the 8th week and 100 in the 10th week, that's about all, and nothing is available on hand. So our net requirements are 50 and 100, and what we will have to do is for product 1 you will have to, because the time required for assembly, the lead time is 1 week, therefore you have to plan for order releases 1 week prior to this, that means in this period 50 and 100 here, okay, which means that we have here, this is 50 and 100 here. So what does this mean? This means that we have said that our order release for these items, if we require them in the 8th and the 10th period respectively, must be initiated in the 7th and the 9th period, and these are the quantities which we have directly, that's all. Similarly for product 2, our requirements are 70, 80 and 25 in the 7th, 8th and the 9th week. Nothing is available on hand, so it directly translates into the net requirement, and again the lead time required for assembly of part P2 is 1 week, so you offset, this is called offsetting. That means this 70, 80, 25 is offset by 1 week. Had the lead time been 2 weeks, then you would have had to offset it by 2 weeks, and so on. So this process is called offsetting. You have this list here, and then you say, in order to meet this requirement you must plan your order releases well in time. So you place an order at this time and this time, only then you will get it here. So it's like working backwards. So we have done this for requirements of product P1 and P2. Now we can look for the assembly, sub-assembly S2 and sub-assembly S3. See, what you can see is, if you look at the BOM, the sub-assembly S2 and the sub-assembly S3 is here. We will demonstrate these computations for the lowest level of only M4, right, which means we will have to calculate S2, S3 and the various components here to be able to arrive at the value for M4. So that is why we are illustrating that how will you compute the requirements for sub-assemblies S2 and S3. The requirements for sub-assemblies S2 and S3, sub-assemblies S2 and S3, how will you find out the requirements for sub-assemblies S2 and S3? Let me explain to you. This is S2. We have already determined our requirements for part 1, and 2 units of sub-assembly are needed in each unit of part 1, isn't it? So what we will do is, we will find out the requirements of part 1 which we have already found out and just multiply it by 2. This is called parts explosion. What we are doing is actually called parts explosion. So what happens is that you have sub-assembly S2, and as far as the sub-assembly S2 is concerned, the product P1, which is the one that you have just computed in the 7th and the 9th period, 50 and 100 is the requirement. So what you will do is double this requirement for the sub-assembly S2, so this will become 100 and 200. So that is exactly what has been done here. So the requirement for the sub-assembly S2 is 100 and 200. Nothing is available on stock, so this is 100 and 200, and this has a lead time of 1, so we offset it. So the moment we determine the requirements of a particular sub-assembly by multiplying the requirements of the previous parent product, that process is known as explosion. You are actually exploding the requirements of the previous product and then finding out these values and this. Similarly, the subassembly S3, it has these requirements. Now subassembly S3, you require only 1 unit of the subassembly S3 for each product. So these are the requirements of the parts P2 which come as it is, and then you can determine the net requirements and then you can offset it by 1 week. So the planned order releases for the subassembly S3 will be 70, 80 and 25 in the period 5, 6 and 7 respectively. So what we have seen is that from the original requirements of products P1 and P2, we have been actually able to determine the requirements at a lower level, which is the subassembly level, and the two subassemblies S2 and S3 we have actually been able to determine from here. Now then our basic idea is that once we have determined the requirements for S2 and S3, we would actually like to find out the requirements for C4, which is this component which is common to two different products, and at the same time we would then want to determine the material M4 which will be occurring here as well as here. Okay. So when you are talking about the component C4, the component C4, now this actually indicates the concept of explosion in a much more dramatic form. When we are trying to determine the requirements for C4, what do you see? C4, 2 units of C4 are needed in each assembly S2, right? So we take the requirements for assembly S2 and multiply this with 2 across the periods and we will get the requirement for C4 from here. But this C4 that you are talking about here, just 1 unit of C4 is needed in one assembly. So what we will do is, we will have to multiply by 2 the requirements of S2 and to get this particular value, and then simply add this requirement of S3 just once. Okay, this is what will have to be done. So that's precisely what's being done here. So what you find is that when you take the subassembly S3, for instance, take the subassembly S2 and S3, let's put it this way. This is the subassembly S2. The requirements are for subassembly S2 are 100 and 200 directly, and when you are trying to work out for C4, you will have to multiply this by 2, right? So when you multiply this by 2, you would get 200 and 400 here, and then to these values you should add the requirements for the subassembly S3, which is just a simple requirement of 70, 80 and 25. So 70, 80 and 25 added to the original values of 200 and 400 will lead to 700, 280, 25 and 400. So I hope this process is clear. This is a typical process of explosion. We are finding out the requirements of C4 from the requirements of one particular subassembly and another subassembly where this particular item is used. So you would get requirements like this, and then the net requirements are the same, and this has a lead time. The component C4 has a lead time of 2 weeks, so we offset by 2 weeks, 70, 280, 25, 400. Once we have determined the requirements of the component C4, we can actually utilize this information to compute the requirements for the raw material M4, and coming down to the lowest level now. So what we are simply saying is that as far as C4 is concerned, this is fine, and this is now how C4 and M4 are placed. Each unit of M4 is required in a unit of C4, and here of course what is really required is that you have each unit of M4 will be required in a unit of C4. So what we can do is the total requirements for item number M4 will be whatever has been computed already for component C4, so which is 70, 280, 25, 40, and then the scheduled receipts for this component are 40. We had seen that we were expecting a consignment of M4 in the third week. This information was known. So you have this here, and on hand for this item is 50. So that means you will get 90 here, and when you get 90 here, what it means is that you can take care of this demand of 70 in this particular period, and 20 will be carried over to the next period. And when you carry this over, your net requirements now will be minus 20 indicating that you don't require anything, because your net requirements are 70 and you have actually 90 available. So this is minus 20, and then 280 you have 20 available, so 260. So this is called netting, the net requirements. And then the planned order releases, this is not an order release, this is an excess, this 20. So if you take it by 3 weeks, because the ordering time for M4 is 3 weeks, so we offset this. So we have 260, 25, 400, and of course this period you don't have to take into consideration because this is an excess. So this gives us the planned order releases for item number M4. Something similar can be done for each component, each subassembly and each part. And the information therefore that you are getting is, for each component or each raw material, we are finding out how much of each of these components are required in different periods, different weeks, similarly here, right. So I think that essentially gives you a summary of how the computations are to proceed in terms of the various products that we have at our disposal. Now let's try to look at the various kinds of output reports which are typically being produced by any MRP system. The primary outputs from any MRP system are actually summarized here, and the first bit of information that you get from this system is you get order release notice to place orders that have been planned by the MRP system. That's the first thing that it tells you. In fact, it tells you how many items are required in each period, right. So the moment the lead times for those items are have been encountered, you can actually automatically initiate a purchase order for each of these items and purchase an item for each of those items. And especially in a situation where you have tens of thousands of items, that means automatically the computer would place an item, would place an order for each of these items whenever this is required as per the MRP schedule which is determined. Because this is the information that you get, right. You recall, that's what we mean. We ultimately get planned order releases, which means for this component you need to place orders for 260 in the first week, 25 in the second week, and 400 in the third week, and so on, right. So you have this information for each item. So this is something that will guide you for material procurement and material requirements. Why is it called material requirements planning? You are determining the requirement of materials in different periods, like we showed you. That's what the idea is. And the reports showing planned orders to be released in future periods. This can also be done, because it's not only the orders that you have to place, but also planned orders that have to be released in the future periods. If for instance you are currently in period 1, it tells you that in future periods 2 and 3 you have to place orders for 25 and 400 of item M4. You can have rescheduling notices indicating changes in due dates for open orders. What does this mean? What can be done is, for instance, that suppose there is a change in the due date of a certain order, right? You wanted 20 cars in January, now you don't want 20 cars in January, you probably want 30 cars in January. So there is a change in the MPS. So then again you can run the MRP system again and do this rescheduling notices, which will tell you what is the additional number of items that you would require of different types for various kinds of open orders. This information is available. Cancellation notices, if the demands are cancelled, including cancellation of open orders because of changes in the master production schedule, this can be determined. And then reports on inventory status can be made available to you directly from an MRP system. These reports, what we called primary reports. Primary reports meaning that they are generally the kind of reports which are generated by any MRP system. And then of course you can generate any number of secondary outputs. Secondary outputs are generally those outputs which you generate on the basis of specific requirements. So these are custom made to the requirement, right? If you have a certain report, for instance, what will happen is that performance reports of various types like costs, item usage, actual versus planned lead times and other measures of performance, this particular report can be generated because the data would be available in the MRP system. Exceptions reports showing deviations from schedule, overdue orders, scrap and so on could also be obtained from an MRP system. Inventory forecasts indicating projected inventory levels, both aggregate inventory as well as item inventory in future periods, these could be made available to you. So depending upon the need, you can generate a large number of secondary outputs from the report, from the system that you have. What are the typical benefits of an MRP system? You now have an idea of what an MRP system does, starting from the master production schedule, the BOM and the inventory status, and then through an example we have tried to look at how you generate the requirements of the parts in different periods. So the next thing would be, what would be the benefits of an MRP system? Some of the major benefits of an MRP system are that there is typically reduction of inventory from 30 to 50% in work in progress. This is what has been reported in the literature. I think this is obvious because when you are actually calculating how much you need and you are ordering on that basis, that means you are not ordering unnecessary amounts which you would otherwise have ordered. That is why there is a reduction in inventory. There is improved customer service, late orders have been reduced by 90%, quicker response to changes in demand and master schedule, greater productivity, reduced setup and product changeover costs, better machine utilization and increased sales and reductions in sales price. Because when there is an increase in sales, you can offer the advantages to the consumer and bring down the prices. So this has been the effect of, these are some of the major benefits of an MRP system which is involved here. Now the MRP system that we have discussed is the basic system which talks only about determining the material requirements. That's why it's called material requirements planning. But there is an evolution of MRP that has taken place. What is the evolution? The first thing that happens with a typical MRP system is that it becomes an improved ordering method. You tend to order things only when you need them. So you are progressing towards, in some sense, just in time. Right? So this is becoming an improved ordering method. And then you can talk about unrealistic machine schedules, ignoring plant capacities, and therefore you can do priority planning on that basis in the second stage of evolution. And then when you graduate further, you can talk about what is called the closed loop MRP, which is not only plans priorities but provides feedback to executing the priority plan. See, for instance, the major defect with the MRP system is, once you calculate the material requirements, you do not know whether you have the capacity to actually deal with those requirements because there was no capacity check. So here we are making those checks, and ultimately in trying to integrate everything, we come to what is known as MRP2. MRP2 is actually called manufacturing resource planning. Manufacturing resource planning. And when you are talking about manufacturing resource planning, basically you are linking the various functions of the organization: capacity planning, inventory management, shop floor control, and MRP. So links up the closed loop MRP with the financial systems of the company. In MRP, material requirements planning, we haven't done any financial linkages. So this links up the finances. So then it tells you exactly how material is flowing, at which point maximum value added is taking place, and things of that kind. That would be manufacturing resource planning, right? So we would talk about these kinds of things. There are typically 4 classes of MRP users. These are like users who become mature in the use of MRP. So the 4 classes are A, B, C and D. Actually you start with class D, then graduate to C, then come to B and then come to A, right? It's like saying that if you were to practice on a PC, you would start as a D class user, then become a C class user, then become a B class user, and ultimately you would become an A class user. So typically A class user, which is the best, would mean that you would tend to use closed loop MRP, you would have integrated systems, you would help to plan sales, engineering, production. So you're talking about integration of various functions, and there are no shortage lists to override the production schedule. That means your production scheduling is so good that you are not deviating from the production that you have planned in class A. In class B, the system has MRP, capacity planning, but no vendor scheduling. Vendor scheduling is not a part of this. Used as a production control system, needs help from shortage list, inventory higher than need be. So we have not talked about integrating vendor scheduling here. That means when should which vendor place an order. Then class C would be system used for inventory ordering rather than scheduling. Scheduling by shortage list, and master schedule would be overloaded. And similarly the class D user would be one who is just using the MRP system as a data processing department only. Inventory records are poor and you are relying on shortage lists and expediting rather than MRP. So this would be the typical users for this. However, when you talk about MRP2, that is manufacturing resource planning, it is an operational and financial system which does company-wide operations, and it is also a simulator, which means that it talks about answering a variety of what if questions. Finally, let's try to summarize what we have done today. We have seen the difference between dependent and independent demands. We have seen that MRP is useful for planning requirements of components and parts, knowing end item demands. And the major inputs to MRP are the master production schedule, the BOM, the inventory and the lead times. That's what we saw. And the MRP logic goes through operations like explosion, offsetting, netting and lot sizing in a bid to determine the requirements of the various parts and components which are there in that particular thing. And finally, some of the major benefits of MRP include improved planning, lesser inventories, shorter lead times. However, MRP does not integrate cost functions. That's a defect. And MRP2, which is manufacturing resource planning, links the financial functions across the organization. So we have seen that essentially MRP systems are valid for dependent demand situations, and through an example we try to show how the basic computations can be made. Thank you very much.